Hello everyone. In this lecture we're going to start discussing a new component. So if you recall, we started by talking about sources. So we talked about sources of energy, included voltage and current sources, both dependent and independent. Immediately after that we talked about resistors. Last few lectures we have discussed capacitors, and now today we're going to discuss inductors, which are another new component that are important in electrical circuits. And we're going to start discussing a little bit about the physics of the component, introduce to you what the equation for the component is, the equation that defines the relationship between the voltage that you apply across the component to the current that is passing through it. And we know by now, once you have that equation, then you can start analyzing circuits that include inductors in them using the algorithm that we have always used. Now, I actually put in all three important components that are used mostly in this course here, and I'm going to start by discussing inductors first and kind of then go back and compare and contrast inductors with the two other type of components that we already know about. So with an inductor, physically speaking, inductor is basically a conductor that is brought into a specific shape to strengthen the magnetic field that is going to be created as a result of the current that is passing through the conductor. Generally speaking, once a charge starts moving, as soon as you have a moving charge, there would be a magnetic field associated with a charge in movement that corresponds to that the movement of the charge. But so as soon as you have a conductor and there is a current passing, there is a magnetic field that is going to be induced around that conductor. Now, that magnetic field is going to conserve energy in the form of magnetic energy, right? And how much of the energy is going to be conserved in that form as a result of a unit current passing through the conductor, the linkage between the charges passing through a conductor and the magnetic field that is created as a result is represented by a concept that is called inductance. So associated with any inductor, therefore, you can define an inductance. Now, normally just a simple conductor at relatively low frequencies is not going to have large enough of an inductance that is important to be considered. That can change when you go to higher frequencies, and that's true not only about the inductance associated with the conductor, but also capacitance and resistance. But nevertheless, you can you can change the shape or form of a conductor in order to magnify the linkage between the current that is passing through the conductor and the magnetic field that is created as a result. For example, if you start looping the conductor around a cylinder, then the magnetic field that is associated with each one of these loops is a certain value, and when you put these loops one after the other, the magnetic field associated with each one adds up, because they're going to end up being all in the same direction. It's just going to add up, and then as a result, for the same amount of current that is passing through that conductor, you end up getting a much stronger magnetic field that conserves the energy, and therefore the parameter that represents that coupling between the current that is passing through the conductor and the magnetic field is going to increase, and that parameter, or that is what we call the inductance associated with that piece. So normally, therefore, the component inductor is shown with this symbol that resembles a piece of conductor that is looped and turned around in a way that the magnetic field and it's just much stronger than just a piece of wire passing. There's the right-hand rule, and based on that you can tell which direction is the magnetic field as a result of a current that is passing through. Let's say if this rotated this way, then if the current is going this way, if the current is going, so just quickly, if this is the loop, it's going, so and the current is going this way, you can hold your hand and basically realize if this is the current, then the magnetic field is going this way. If this is the current, then the magnetic field is going the other way around. That's really not important for this discussion. This is a discussion for a physics class or electromagnetic course. What matters to us for circuit analysis is this specific equation that then relates the voltage that is across the inductors to the current that is passing through it. And it goes like this. The voltage difference, which we define as the voltage on one side of the inductor minus the voltage subtracted by the voltage on the other side, is equal to the inductance in the unit of Henry. So the unit for the inductor inductance is Henry, times the derivative of the current that is passing through the inductor with respect to time. So once we know that this relationship defines the relation between the voltage across the component and the current, that's really all we need to know in order to be now able to analyze circuits that include inductors. Now, before we do that, and I show you that that's really all you need for circuit analysis, and that's what matters for this course, we're just focusing on circuit analysis. I just want to go a little bit deeper into how inductor and the other components relate to each other, and why do we normally need each one of these inductors in a certain application that we have. So let's quickly actually go from the bottom to top. So with the resistor, which was the first one that we described in terms of the passive components, not obviously sources are active, meaning they actually give you energy. In these components, there is no energy that is being generated, right? So you apply or induce energy to these components by connecting them to a source of energy. Now, with the resistor, if you recall, the equation that defines the operation was something like this. We called it actually the Ohm law. You take the voltage across the component divided by the resistance in the unit of Ohm, and you get a current. Simple equation. It was easy to solve circuits that include resistor, mainly because it was just a simple algebraic linear equation that defined the voltage across the component and the relationship of that voltage to the current that is passing through the component. Now, one thing that is important to realize here is that in this component, the resistor is basically taking that energy that is applied to the component and turning it into heat. Sometimes that's called loss or waste, but that's not generally true, because sometimes you actually want to create heat. Most of the time in electrical circuits you don't want to create heat. There's something else that you're trying to do, but the heat generated in the resistor is the byproduct. So the power that was calculated for the component, which was the voltage across times the current that is passing through it, all that power is actually in the form of heat. So the energy, incoming energy, is in electrical domain. It's an electrical energy. But what happens in this component is that incoming energy, actually all of it, turns into heat. So you don't get any of that energy back. It actually leaves the system in a form that is normally not irreversible, meaning that once that energy is turned into heat, you will not get any of that energy back into the electrical domain. Now, with capacitors, that was not the case. So first of all, the equation that defined the relationship between the voltage across the component and the current that is passing through it was something like this. The current that was passing through the component was the capacitance in farads and multiplied by the derivative of the voltage difference with respect to time. First and foremost, this equation is just not a simple algebraic linear equation. It actually has a derivative in it, and that's where the mathematical complexity came into place. In other words, once you started having resistors in your circuits and you wrote all the equations and tried to solve it, you would reach to basically a conclusion that you have to solve a differential equation in order to be able to find out all the voltages and currents in the system, because of how they're related to each other. The voltage and the current are related to each other. But physically speaking, what we said is that by applying the voltage, you're going to get charges being collected on the two conductors, plates that are really close to each other, and that creates an electric field, and that electric field actually conserves energy. In other words, the energy that is applied to the capacitor, it is conserved on the capacitor rather than being consumed, as was the case for the resistor. In other words, that charge, if you take that source away now, that charge is going to stay there on the two electrodes, and if you want, you can actually get that energy back by taking that capacitor and connecting it to something else, like a load or a resistor. So you get the energy back in the form of a current or an electrical domain. So the fundamental physical difference between a capacitor and a resistor in that sense is that the capacitor is conserving electrical energy, as opposed to the resistor, where the energy was being consumed or turned into heat, which is not an electrical domain parameter. What conserved the energy in the capacitor, though, was an electrostatic field. Now, when we look at the inductor, the current that is passing through the conductor generates a magnetic field, and this always does. That magnetic field now conserves some energy. But this energy is associated to the movement of the charge, as opposed to the case for the capacitor, which was just the energy was associated with the field, electrostatic field, that was created as a result of the charge being accumulated across these two. So here, the conservation of energy had nothing to do with the movement of anything, specifically not movement of the charge. Whereas here, sorry, the energy that is conserved is in the form of magnetic field, and that energy is associated with the movement of the charge. So here you have to have a current in order to conserve energy. Here you had to have a voltage or charge to have. Why am I saying that? Because with the voltage you get an electrostatic field. With this one, with the current, you get a magnetic field. So you kind of see a duality, physically speaking, between the inductor and capacitor. And that duality immediately shows up in the equations too. In other words, with the capacitor, current was something times derivative of a voltage, whereas in the inductor, the voltage is actually something which we call an inductance times the derivative of a current. So you clearly see the duality between the two. Here, the conserved energy is associated with the charge or voltage or electrostatic field. Here, the energy conserved is associated with the movement of the charge or the current that is passing through the conductor. Okay, all that said, I think we're ready to now show you that all you need is that equation. And obviously, like what we did with capacitors, we're going to start after finishing this lecture, we're going to start analyzing circuits with the inductors. But for now, I'm just going to take this very simple circuit, use that equation, and show you how you approach a circuit where there are inductors included. In other words, I'm going to show you that there's nothing different in terms of how we approach the circuit. So how did we do circuit analysis? We started by labeling the circuit. So this is one node, one node, one node. I'm going to assume that's my reference. That then at that point would be VST. Why? Because that's the equation for that component. I'm going to call that V1T. Notice I keep on putting time here to kind of remind myself that currents and voltages here are going to end up being a function of time. Okay, now the currents, if I call that IST, writing the KCL in my head for that one tells me that this one is also IST, and writing the KCL for that node would immediately tell me that this one also is IST. So with that, I don't have to write a KCL anymore. Obviously, this was a really simple circuit, but by now you should be able to do this. So once I do that, then I start writing equation for components. So equations for components, there are 3 components, but I already wrote the equation for this component, so there are 2 equations left. Equation for the resistor is already there. IST is equal to VST minus V1T divided by R. Equation for the inductor is what is here, which says voltage here minus voltage here is equal to the L times derivative of I. So that would be V1T minus 0 is equal to L d IST dt. And that's it. Now I can start writing doing the math in order to find an equation that would include only one unknown. And once I have that, then I'm done. Okay, so this is really simple. Obviously, I take V1T in this equation, put it there, move that to the, so RIST, writing that equation, is equal to VST minus LDIST dt. And that's it. So IST dt. I'm just moving the equations things around. Plus RIST divided by L is minus VST is equal to 0. So in this, the only unknown is IST, and in order to calculate IST, obviously I have to solve a differential equation. Now, how do we do that? Obviously that depends what VST is, and we're going to start doing that. We're going to start by using normal DC sources first, and you see that you can turn this equation immediately to the form that we already know how to solve the first order differential equation, and then the solution is basically the same that what we saw. The parameters that we have, K and tau in the circuit, are going to be different, but at the end of the day, how we approach it is exactly the same. And once you have IST here, you can put it back into any of these equations and get V1T, which is the only other unknown in the circuit. And once you have that, everything about the circuit is known. Okay, so with that, I'm going to finish this lecture. I guess by now you know that every time that we start talking about a new component, all really we need to know in order to be able to do the analysis is to know the equation for the component, and then everything goes back to the normal algorithm that we have. I'll continue talking about inductors in the next lecture. Thank you.